So let me start. So let me start today's seminar. Our speaker is Danilenko from UC Berkeley, and the title is Stable Envelopes from 2D Mirror Symmetry. Vanya, please.
Yeah, so I want to mention that this is part of joint work with Andrey Smirnov, which branched out of a big ongoing project with Mina Aganagic, Yixuan and Peng. So let me start with what stable envelopes are. So let me start with a smooth algebraic symplectic variety over complex numbers. And I will act by a certain torus on it. Algebraic torus section. And because my variety is algebraic symplectic, I want this torus to somehow respect the symplectic structure. So I have the algebraic symplectic form on X, and we say that it is an eigenvector of T. And so it scales it with certain character, with non-trivial character. Which I'll call H bar. Okay. Then we have a subtorus of T, a subgroup inside of T that acts by symplectomorphisms because it's the kernel of H. So it acts by symplectomorphisms. Okay, so my favorite easiest example is when X is cotangent bundle to P1, then the usual symplectic structure turns out to be holomorphic algebraic. And we have two-dimensional torus action. There is symplectomorphic torus that acts on P1 by scaling, and hence on T star P1, right? And there is an auxiliary action which scales the fiber, scales the fibers. And the combined torus is the symplectomorphic torus and the scaling torus, right? Okay. Now, when I start to do equivariant key theory with respect to this torus action, I see that after localization, my key theory turns out to be to have certain bases corresponding to the fixed points. So the fixed point basis is the easiest one, but I'll be interested in slightly different bases. let me try to describe what is this one. So for every, so in what follows, we will assume that the fixed locus is finite. Because in our examples, in the second half of the talk, that would be the case. So then for every point, every fixed point A, and the choice in a character of A, we have attractors with respect to attractor to the point with respect to the co-character. So I have my fixed point and something is attracted to it.
When you say attractor, you mean positive time, negative time, so it's kind of to fix.
Just pick your favorite convention. It will just redefine what is sigma and what is minus sigma here. Just in what follows, I will try to consider generic co-character, and the positive character would be as good as negative character. Okay, so for me, attractor depends on this choice of co-character. So because we have symplectic structure, the tangent space at P splits into two parts. One is positive with respect to sigma, and the other is negative. And they are isomorphic, right? So it means that these attractors are of dimension that are half dimension of X, right? And you can even show that they are Lagrangian, even Lagrangian. So dependence on generic sigma is locally constant in if I consider the space of co-characters and formula tensor with Q. There is a hyperplane arrangement. So let me make it more precise what we mean by generic. So there is a hyperplane arrangement. In this space. And in every chamber, attractors stay the same. So that's why instead of just fixing a co-character, we will write attractor with respect to certain chamber. So this is a chamber. So there will be like finitely many options how we can define what is an attractor, and they will depend on certain chamber in the space of co-characters. Okay, going back to the example. Before that, let me say how is it related to the stable envelopes. So idea of stable envelopes is to refine the class of the structure sheaf of the attractor to a point. So it turns out if I take attractor or its closure and take its structure sheaf, it's not good enough object for us. And I'll show in a second why. Okay. So let's do the example of T star P1. So I have exactly two fixed points, 0 and infinity of the 0 section. So I will schematically draw it as I have 0 section. I have two my favorite fixed points, 0 and infinity. And also I will draw what happens in their fibers. So this fiber is cotangent fiber to 0, cotangent fiber to infinity, and here is the 0 fiber. So there are two chambers, or two chambers. I'll call them positive and negative one. And I'll define the positive one to scale like this. So once I know how it scales P1, everything else is uniquely determined. Okay. So this is scaling in this chamber. So now we can write explicitly what are attractors here. So attractor with respect to plus chamber of 0 would be everything that is contracted to 0. That's only the fiber. And the attractor to infinity will be the whole P1, excluding 0, actually. But let me just write it like this. Right? So that's if we try to do it in the easiest possible way, but it turns out that these objects don't behave quite well if we try to perturb our situation.
So which object doesn't behave well?
I'll show in a second. The second attractor will not behave well.
So can I ask I think I missed in the beginning, everything here is algebraic, so the symplectic form is holomorphic.
Holomorphic symplectic form. Yeah.
So these Lagrangians are also complex. Okay.
Yeah. Yeah. Mm-hmm. Right. So we can do deformations of this as an algebraic symplectic variety. And it's known that there is a universal family of deformations, which is one parametric. So we have at our 0 of this parameter, we have our T star P1 thing, and somewhere away from it, we have deformed code. Maybe a better way to say it, T star affinization of T star P1 is the nil cone of SL2, and if we deform the cone, we will have deformation of the symplectic variety.
So to understand, you consider T star of P1 as a Springer resolution of the nilpotent cone, and you deform the nilpotent cone. Is it what?
Yes, that's one of the ways to see it. If you prefer Nakajima equivarieties, you can also say it in terms of Nakajima equivariety. There is an extra parameter of deformation there.
Can you say it? Because there are graduate students. To them, I give a course on Nakajima's book. They will be happy to see you. Okay,
so Nakajima equivariety description of T star P1 would be to take the quiver of this form, and then you take the preimage of 0. Sorry. Okay, so the center of the group by which I quotient, and actually it turns out it's a abelian quotient, it is everything. It has one parameter psi. So instead of doing just preimage of 0, I can do preimage of zeta, and then take the GIT quotient with respect to the action of my group, which is GL1 here. So GL1 acts here. And also I need to take points semi-stable with respect to, and when I take this quotient, I actually need to take it with respect to a certain character. So usually that's called Nakajima equivariety with this thing. So I get T star P1. T star P1 is when zeta is 0 and theta is not 0. Oh, sorry, it will be positive. If I take the negative one, I'll take T star of the dual P1. So this is the how you get the family. You automatically allow zeta to be anything, and if you explicitly write down what it is here, you will see that when zeta is not 0, variety is smooth affine. Smooth affine symplectic. Okay. But because it's affine, it cannot have holomorphic curves inside of it. So essentially, what do I see? I see that over my 0 point where I had T star P1, I had the attractor that was a holomorphic curve that was attractor to infinity. And if I deform it, the variety as this thing as real manifold stays the same because we just have a family of smooth real things. But the complex structure and symplectic structure deform in a way that I cannot have holomorphic curves in it anymore.
So this I kind of not I'm telling that I do not understand, but you said something about real. There is nothing real for me. It's everything.
Oh, I can just take
holomorphic.
underlying real manifold.
Ah, okay. Yeah, all right.
And because it's a family of smooth real manifolds, there is no way just topology or anything of it changes. It's like trivial. So the only thing that varies in this family is complex structures and symplectic structures.
Yeah, you are saying that as a real manifold doesn't change, but holomorphic complex structure gets changed. Is it what you
Right,
say?
right,
Okay.
right.
Okay.
Yeah. And basically we see if I'm trying to plot how my attractor now looks in the deformed one. So let me draw these things, even though now they are not. These are like corresponding real things if I trivialize my family as real manifolds. It now looks that my attractor goes to infinity here. I slightly perturb the data and it cannot end on the other point. There are no holomorphic symplectic curves. It has to escape to infinity then. Is it clear? So my small perturbation of a manifold of this holomorphic symplectic variety gives me that these attractors start to behave. They have big changes in them.
So both of these attractors for zero as well deform like this, or?
No, for the other one, it will more or less be like the fiber. So the other one behaves well.
So this is like some kind of a spherical twist, or is that?
It is related to spherical twist, but I'm not saying it like this. Okay. Yeah, it is, especially in this case, because yeah. What else could it be for cotangent bundle to S2?
Yeah, actually, there is kind of a more complicated model for that, where at zero you put a modular of Higgs bundles with a cis direction, and at z is not equal to zero. It's a character variety, and so then. Of course, the cis direction being translated to the character variety from modular of Higgs, it becomes quite complicated. So kind of what was, I mean, it's subject to this non-abelian Hodge theory. Yeah, okay.
Yeah. So from this consideration, we see that the correct version, the corrected version of attractor to infinity should be the limit. Be the limit of what we've had here. So in cohomology, in equivariant cohomology, that would be just the Poincare dual of the attractor to infinity plus the fiber, so the attractor to zero, right? Because we see how they deform. There is something that spans once the zero section and once the fiber over zero.
So first of all, you will consider these attractors as what? So it looks like you consider cycles and equivariant cohomology, but
yes, but that's the motivation. Then you can upgrade it into equivariant K theory. So the original construction by Molly-Kochenkopf was in equivariant cohomology, but then it turns out that you could lift this definition into equivariant K-theory. I don't want to go into technical details.
But what's the definition? So what I understand that it should be a limit, but what kind of limit? What is actually?
Yeah. So the definition tries not to deform it. So it is true that it comes in families, and in families it behaves well, but the definition tries to do it only at one fiber. And okay, let me try to write what how to formalize it. So we say that stable envelope is a map So I will write it in equivariant key theory. So it looks like it's a wrong way going map. The usual map that goes here is a restriction map that goes the opposite way, and we're trying to map it back. So it is of modules over our ground ring with properties such that support of stable envelope. So as I said before, attractor depends on a choice of chamber. So support of stable envelope of O of P is on the union of all smaller attractors to Q with respect to C, where Q is smaller than P with respect to chamber C. So my points here have some order induced by the action, and in this picture, zero will be smaller than infinity. So that's why when I compute stable envelope for infinity, it could have support not only on the attractor to infinity, but also on the attractor to zero. Then second of all, we have some normalization condition. By setting that stable envelope of a point restricted back to this point, or let me write restriction to the point by just telling pullback, is some explicit.
So, sorry, I missed the notation. State COP. OP is what?
It's the structure shift of a point.
Structure.
So
okay.
it's an object that lives here,
okay.
Right? And so basically everything here is just a collection of these guys, their bases, right? So I'm just saying where the basic guys goes. So I also call this stable envelope of the point P. So to simplify notation, I'll later call it step C of point P. So second condition is some sort of normalization condition, which basically says that if I sit at my point, the restriction to this point will give the same contribution as just the attractor here. It's some explicit expression in the conormal bundle, in the conormal fiber at this point. And the third thing is that the elements that are, so this condition implies that the restriction matrix, let me write it. I have restriction matrix is triangular with respect to the order given by C. And my second condition fixes what it is on the diagonal. And the last condition is that off-diagonal terms of the restriction matrix are small in certain sense. So if we go back to our definition as a limit, we will see that the two things that come to 0 will introduce some partial cancellation there, and it will be a small term. Okay. Are there any questions about this?
Yeah, of course, in this sort of condensed way, it's difficult to understand what's really going on. So basically, you have a diagonal, you have a different basis, different from a Tia bot, and this.
Yes, it will become a basis after localization, basically because it's upper triangular, and there is some sort of change of basis here going on. And it's convenient that these guys are actually not localized. So especially when you're doing it in cohomology, just you can use dimension axiom and everything becomes much more controlled. So this type of definition was given by Molly-Kochenkov. For equivariant cohomology first, and that gives geometric theory of R matrices acting on equivariant cohomologies of Nakajima equivalents.
Which are matrices?
So basically, for Nakajima varieties, let's consider the special case, like just frame.
No. In general, the question is general, not so. You start with a quiver. In examples, I can imagine what you get.
Just it generalizes the R matrix for skin chains. There is some sort of auxiliary space, and there is some. You take a quiver variety. You act by some special character that splits it, roughly speaking, into two halves. One of them you think about as auxiliary space. The other is like actual space that you want to study. And you construct R matrices from stable envelopes by taking like stable envelopes and inverse of stable envelopes with respect to different chamber. And it gives you transfer matrices. It gives you action of Yangians or some for key theory quantum groups.
And they act on what? Because it looks like you get the basis, so it's finite dimensional.
No, this basis is required to construct our matrices. R matrix that goes from chamber C to chamber C prime. It's stable envelope with respect to prime chamber, stable envelope C. So if you define this change of basis, but like from one type of this different basis to another type, it turns out that they behave like R matrices in spin chains.
So I have no idea what spin chain is. I'm not a physicist, even not a mathematical physicist. So it's some map in what? In modules of finite type over, say, equivariant cohomology of a point. And so are they infinite dimensional as vector spaces?
It is a map from equivariant, let's say, cohomology to itself. And they satisfy Young-Baxter equation. Or more precisely, generalized Young-Baxter equation, because here your hyperplane arrangement is not necessarily of type A.
Still confused, because you can write down the quantum R matrix for any quantum group. All right, this is okay. If you take homology, it's probably some rational version. If you take a theory, it will be
exactly, and the rational version is Yangian. But basically, Molokov go the other way. They say that the thing that respects R matrix is a certain quantum group, and actually can be extracted as certain matrix elements in R matrices, and that's actually how, to the best of my understanding, quantum groups were invented. They're controlling some sort of statistical system where R matrices appear naturally. So they follow like the same historical logic.
Yeah, okay. So then it's basically R matrices for the Yangians corresponding to arbitrary or whatever quivers, not necessarily GLN is what historically invented.
Yes,
okay.
Yes. Yeah, so that's their approach. And I mostly mention them just to say that stable envelopes are valid, basically. So these classes appear in to make a geometric representation theory story for equivariant cohomology or equivariant K theory of symplectic resolutions of algebraic symplectic varieties of certain type. Here it was like quiver varieties, but we could do it for other varieties as well.
Yeah, and you said that these stable envelopes, they enjoy some nice properties with respect to deformations, and somehow I missed what these nice properties. I feel I should be happy, but I'm not sure about what. What are
symplectic resolutions come in families, and basically you could try to define your stable envelope in the family, and the coherent way to define it in the whole universal family of deformations of symplectic resolutions should be this. But after that, you try to rephrase it that you care only about what happens at the origin of your family for your original symplectic resolution.
And so what, so I'm still missing, and if you consider the, say, universal family, so what's happened with these stable envelopes? Do they, so that's the example which you shown for T star of P1, but what's a general statement?
So just the general statement is that these conditions which we write here ensure that you can extend it to a deformed version as well. We will have some classes for deformed version.
And they behave well in, okay, all right. Mm-hmm.
Yeah, but I don't want to go into details how it works, just because,
it's not a subject of your talk, but thank you.
So yeah, and as we said, after localizations, this is a basis, and there is a standard fixed point basis, right? Push forwards of structure sheaves of the point. So we can ask how to write stable envelope of a chamber C of point in the basis that is structure sheaf of fixed points, right? Or what is the transition matrix between them? So it is enough, but by localization theorem, it's enough to compute restrictions. So the restriction matrix knows about the whole class. So where Q is my fixed point and IQ is the inclusion of this point, right? And I can compute it by Mukai pairing. So we can find it by computing the Mukai pairing. So Mukai pairing is the earlier characteristic of R Hom, of the derived Hom, in the category. So I will write here as coherent sheaves of a point. So that's basically the same as computing the pullback up to taking a dual. So up to inverting characters. That's exactly what we're computing. And that means that I can do the same by taking an adjunction. I could take R Hom in coherent sheaves on X between stable envelope and the push forward of a point, which we call by the same name. Right? So if we know how to compute R Homs in the category, we will be done here. It doesn't look like a simpler task, surely, but we will see that for some reasons, after mirror symmetry, we can compute them more effectively.
Well, then you should explain what do you mean by mirror symmetry.
Yeah, we're going there. We're going there. But before I do this, I need one more auxiliary space. So for our purposes, it's convenient to replace coherent sheaves on the whole space X by a derived category of a smaller space. So the space, which I'll denote by straight X, it is just the union of all attractors with respect to all chambers and all points. So for T star P1, that will be exactly the three things I drew. It will be two fibers and the zero section, right? Because
Sorry,
Yeah.
should this be thought of as a skeleton of the?
Yes, it's like Lagrangian skeleton or the core. So we will call it, the core of X. So it is Lagrangian at a smooth point, and so it is mildly singular, but it's an invariant holomorphic Lagrangian. Okay. And why is it valid for our problem? Because I know that I want to compute our homes between two classes, and these two classes naturally come as push forwards from the core. So stable envelope by definition and fixed points come as push forwards. Along the inclusion of my core to the space, right?
But so the subcategory is the category of objects supported on the core, or is it sort of the?
No, it just the morphisms change, right?
Okay.
So it's not subcategory. It's
Okay.
right?
It's like the category of objects on X.
Yes, it's category of objects on X. So we consider then coherent sheaves on X. Okay, and it's not subcategory. So we can compute.
Well, X is singular. This X.
Yes. So let me just be a little bit sloppy here about what actually I mean here by. Okay. In principle, just yes, it's a category of coherent sheaves. You can define it. Okay, so we can compute what we had before, like this thing. Again, by just so what I had before is our hom. Right? And actually, let me from now on denote by these simple symbols the objects that live here. And for their analogs in the bigger space, I will denote them by just push forward to them. Right? I want to compute this, and this is just Euler characteristic of our hom. Of pull push stable envelope as an object on coherent sheaves on the singular X to the structure sheaf of the point. Okay. So my claim is that for some, surprisingly, this is easy to compute, relatively easy to compute via mirror symmetry. Can I proceed, or are there questions about?
Yeah, you better proceed because you know the time is kind of limited.
Right. So our example would be that X is Coulomb range of n equals 4 3D gauge theory, quiver gauge theory. And for simplicity, I'll just look at the framed quiver like this. So as before, my symplectomorphic torus will be one-dimensional, and I'll call the corresponding character alpha. And the big torus is just extended by this thing. And examples which fall in this family are, for example, T star P1, but be careful, it's not quiver variety of this quiver, it's Coulomb branch. So quiver variety is Higgs branch, and this is a Coulomb branch, but it turns out to be also in this family. And resolutions of AN singularities. Okay, these are all two-dimensional examples, but they are higher dimensional as well. And Mina Aganagic. In a pair of papers in 20 and 21 predicts from physics the following version of mirror symmetry.
You mean 3D mirror symmetry? It's not.
This is 2D mirror symmetry. So it
2D
would be
mirrors.
coherent sheaves is Fukaya. So 2D mirrors.
Okay.
Yeah, we don't swap Coulomb and Higgs branches. We do coherent is something Fukaya. So the category I care about, derived category of coherent sheaves on the big space, is mirrored, is equivalent to a version of Rev Fukaya category with on some space with a superpotential. And recall that we wanted to find another guy here. And it turns out that it's also mirrored by a certain Fukaya category. And we had natural functors here, the push forward, the derived push forward and pull back. And they're also mirrored here by some functors. Okay, so this side we call B side, and this is A side.
Now, what is written here?
So on horizontal lines, we have equivalence of categories. And I claim that under this equivalence of categories, the functors actually coincide.
So functors coincide. So first of all, your X Carly and X non-Carly, they indeed behave like symplectic manifold, and it's Lagrangian.
Yeah, Coulomb branches are algebraic symplectic, and the straight X is its core. So it is exactly what we talked before. There is a algebraic symplectic, a smooth symplectic variety, and its core. So that's what we saw before was this side. And we want to compute our Holmes of certain classes here that come from these guys, from this category.
So, I ask for the help of the audience. So is there a notion of Lagrangian skeleton for Landau-Ginzburg model, Gabe?
Yeah, sure. I think there's, yeah, if you have a Landau-Ginzburg, you can.
Landau-Ginzburg is here, and it's
right.
not quite. These functors are not skeleton. This guy, open dense part of it, is a C star to some power fibration over Y.
Yeah.
So that's what gives these functors. It's different story, but it mirrors. So inclusion on B side is mirrored by almost having a fibration on another side.
Okay, so yeah, that's still too many questions about how these 4 vertices are defined. Well, on the B side, you can write whatever you want. Like there is a derived category of equivariant sheaves, and you can prove these 2 functors, conjugate. So basically, on the B side, you have equivalence of 2 categories.
No, they're not equivalent.
They're not equivalent.
The K theory is not even the same. Only after localization becomes the same.
Okay, yeah, all right. So then it's no better than, at first glance, no better than localization and then a T-abort, because you also...
Well, yeah, localization would be if I added like also like one side lower, like just the fixed points.
Yeah.
Would go like one more level.
But my question is, there is a notion of localization of categories. So then I'm wondering whether they still become equivalent after localizations at the categorical level.
I'm not sure if it is the case because these 2 localizations are different. And localization of categories, you allow some morphisms to be invertible, and here I allow some elements in the ground field to be invertible, and it only gives isomorphisms in K theory, not on derived level, to the best of my understanding.
Still, I would be surprised if this equivalence in the K theoretical level cannot be somehow lifted. It would be very strange. It may be not just conventional localization like from textbooks, but still.
I'd be happy to hear how it's done. I don't know it.
Yeah, okay. And these Y curly and non-curly, are they kind of constructed? They are conjectured?
Yes, we know how to construct them, and in this talk I will describe what the straight Y is.
Okay, good.
And upper Y will be just like a partial compactification of just a fibration over it. So there is a way how we so we know both guys, and our project now with Mina and other collaborators is to actually prove this categorical equivalences.
Yeah, but you say that this Y non-curly is easier to see, and Y curly is some sort of compactification of C star and fibration, or how it goes?
It's compactification, but we can explicitly write down what it is. I just don't want, because it's not the topic of my talk. It can be done. Okay. So maybe one thing that, because we have equivariant categories on B side, we should do something on A side similar. And in this case, it's multivalidness of superpotential. So T equivariance is mirrored by multivalidness of superpotentials controlled by rank of T parameters. So now in my Fukaya category, the objects will not be just Lagrangians, they will be Lagrangians with some preferred branch of superpotential on them. So that's an extra choice, and this choice is similar to choosing equivariant structure on the coherent sheaf. We can always twist by a character, right? And that will be like shifting the branch on A side. Okay, so our goal would be to, by the end of the day, we want to compute some pairing here that can be rephrased as pairing here, that can be rephrased as pairing here. So the point of my talk is that certain computation on this side coincides with what you can do by other methods directly here. So indirectly, it shows that this picture can be true. Okay, so let me go to description of Y. Of Y straight. So we take a cylinder, or if you want to think about it, C, we've removed the point, and we fix an n-tuple of pairwise distant points. In which we think about them as punctures on our cylinder. And then I say that Y is just unordered k-tuples, like Y1, YK of distinct points in the cylinder with punctures. So I have my, I think here is 0, here it's infinity. That's how I write my C star, like a cylinder. Then I remove some points here, Z1, Z2, Zn, and there are some points wandering around on it without being allowed to collide. Okay, and we introduce a superpotential.
So and just clarifying that N and K are the same as in the representation of a quiver, yeah?
Yes, exactly the markings on the quiver.
Yeah.
Yeah, and I will write superpotential again exactly from the quiver. You can generalize it to any framed quiver you want. So it will be controlled by two parameters, lambda naught and lambda 1. And W naught would be of this type. So this interaction of points with each other plus summation over I and A, interaction between the points and the punctures. And the first one will be much easier. It will basically count going around the cylinder. So it will be the summation of log yi's. Okay. So we see two parameters that are here, and these are exactly the mirrors of characters of torus. So to compare, I will write that e to the 2 pi I lambda naught is alpha, and e to the h bar. This is h bar. And e to the 2 pi I of lambda 1 is the character of A. Okay, so we have identification of parameters here, and Now, if I intersect two Lagrangians, I will not just count how many points of intersection they are. They will also come with some monomial weight in H bar and alpha, which is exactly what we have for equivariant coherent sheaves, because the space of morphisms is graded. And when we compute Hom, it actually comes as a certain polynomial in equivariant parameters. Is it clear?
Well, of course, it's not clear. I mean, the choices are not clear, but there should be some explanation why this bottom line gives you equivalence in your diagram, because you have already defined all the objects, except that you did not quite set what's, how do you understand the Fukaya's ideal category for...
Yeah, it should be wrapped with respect to this superpotential.
Yeah, so...
Yeah.
But, well, yeah, I can imagine that, again, there is some subtlety that your potential is multi-valued. Basically, you are dealing with one form, and so, which means that if you try to prove something, you will have infinitely many, probably Lagrangians, which you should take into account. So kind of infinitely many symbols, something.
But they are the same up to certain shift. So it's like saying that, okay, even in on coherent side, we should consider not just, let's say, fixed points. Even in K-theory, we should consider them multiplied by any character. And that's like infinitely many of fixed points? No, I would not say so.
Yeah, maybe. Let me...
Change of a character, or shifting everywhere branched by something is like autoequivalence of this category, like multiplication by a character on coherent side. It's mild. So at this place, I don't see difficulty.
Maybe go on. I should think of it.
Yeah. So let's do decategorification. So like then. So basically, we apply K functor to both of categories, and for one, we'll have like equivariant K theorem, and when we have Lagrangian plus choice of the superpotential on L, that gives us just a homology class of L, about which we think that it's the middle dimensional homology of Y with respect to local system, rank 1 local system. Local system. With monodromies of e to the W. And so is it clear so far? So it's a cycle on which I chose a section of my rank 1 local system. Basically, that's what I'm saying.
You see, now I'm confused with whether you consider holomorphic or real Lagrangians, because you need to consider a real, yeah?
I need to consider real, right? So holomorphic Lagrangians were on B side. Here I will just consider
it's all on the A side. Okay, good.
Yes, all on the A side, so they are real. And also sometimes I want to allow them to escape to infinity. So I should write some relative condition in partial compactification. or consider something close to Borel-Moore homologies. Just I will need to allow them to go to punctures or to infinitives. Okay. So possibly there is some relative condition here. Okay, which I can introduce by hand later by saying where it can escape and where it cannot. So actually, this space, it appeared long time ago when people studied Knižnik-Zamolodchikov equations and tried to find their solutions by taking integrals along certain cycles. And these integrals were conformal blocks. So this is the space of cycles over which we can integrate, basically. And as far as Mina's logic originally, she was going the other way. She was saying that, okay, we know what conformals blocks are, and we try to categorify them. So we take these contours of integration that appeared in study of Knižnik-Zamolodchikov equations with like exactly this local system and try to categorify them. So we now say that they should be Lagrangians. So we have a Fukaya category. But I'm going like one step back. Let's consider this one. And in planar case, it's definitely been studied to death. When I live not on a cylinder, when I live on a plane, it was a rich source of information about quantum groups, about Knižnik-Zamolodchikov equation and representation of braid groups. Okay, maybe one last remark. This condition actually doesn't matter after we localize. So if we keep monodromies of our local system generic, I can prove that basically you can always make a thing that tries to escape to infinity be represented by something with compact support. So, okay. So now we will match, the localized key theory of the core, or if you want the key theory of the original space, with this homologies, which I will also write log by meaning that localizing with respect to parameters here is exactly keeping them generic, algebraically independent. And here I'm doing the same stuff, basically, when I said that. I want to get rid of them. Okay, and first of all, we need to understand what is the dimension of the space. The dimension on B side is the number of the fixed points, and that's exactly the choose number. Okay, and they are exactly this many cycles in Y of form. So let me draw my cylinder. Here are my punctures. And I'll choose K of them, K points. Let me mark this one and this one, 2. And I will make these cycles. So that will be like F for some choice of subset. S is inside. Right. So this is F of 2, 5. 1, 2, 3, 4. And if we match the structure sheaves of points with this Fs for some identification of points with subsets, we get an isomorphism. Which so far it doesn't tell basically anything except that they are vector spaces of the same dimension. But under this identification, first of all, is an isometry. So the Fourier-Mukayo period, which is the earlier characteristic of the derived Coulomb in both categories, matches. Basically because both of these bases are orthogonal, and you can check what is the norm of each of them and see the matching. The norm is some polynomial in my parameters, and I'll just match them. So it's non-trivial check to see that they coincide. Okay, and second of all, on both categories, I have a fine braid group action. So it identifies a fine braid group action. On A side, it's manifest. We can move the punctures on the cylinder, and all the ways how we can move them is by definition the fine braid group. And on the other side, it's more complicated. It's derived autoequivalences of the category of coherent sheaves. But for K-theory, you could write it in terms of convolutions with Steinberg correspondences, and it is very well known how it behaves there. On the level of K-theory, it's very clear what it is. Okay, so we match these guys, and we see that some important shadows of the categorical structures match. Shadow of Holmes is the pairing it matches, and derived autoequivalence also match. Okay. Are there any questions here?
Well, it's just a statement of results,
Okay.
so we cannot verify it. Now, let me ask you a question. How long do you plan to speak? So
I just want to say what are stable envelopes in this picture, and I'll be done basically.
Mm-hmm.
Yeah, so like 10 minutes maximum. Is that okay?
Okay.
Yeah. So sorry, I have a question. You're not not saying what the action on the B side is because you don't want to go into details, or because it's like it hasn't been completely worked out.
Just because I don't want to go into details.
Okay, thank you.
If you consider T star P1, that's exactly the affine Hecke action of Ginzburg. So, and basically like it's generalizations. So it's in K-theory, it's a very well-known thing. So what are the Steinberg correspondences you need to consider? Okay.
Thank you.
Yeah. In derived case, as far as I understand, it's a little bit more, it's complicated. So Bezrukavnikov has something, as far as I understand, in cases when you do derived Steinberg correspondences, but let me now go there. In K-theory, it's known. So, and this information, this gives enough information to prove that cycles so again, they'll correspond to some choice of my punctures. But now I'll go not around the cylinder, I'll go to 1 infinity. So that will be S plus of certain subset correspond to stable envelope plus a point. And if I go to the other infinity, to 0 in this picture, that will be the minus stable envelope. Stable envelope minus correspond. Basically, here we can verify that the diagonal terms are the ones that are prescribed by definition, and then use the affine braid group action, or here it factors through affine Hecke algebra action, to show that the restriction formulas satisfy certain recursive relations on both A and B side. Right? So we see what are stable envelopes after applying mirror symmetry. There are some very explicit cycles on a quite natural space, which appeared, once again, when people tried to study Knižnik's homological equation a long time ago. The only thing is that they studied it on a plane, and it's not how it comes here in mirror symmetry. In mirror symmetry, it comes on a cylinder. And these are the natural objects in this world. Maybe one last remark. When we prove the categorical equivalence, and once again, it's a project with Mina and co-authors, we can say that the cycles I drew here are certain Lagrangians. So they're well-defined objects in Fukaya category. So after mirroring, it should give the derived, the categorical version of stable envelopes, not just as classes in K-theory, but as honest, derived coherent sheaf. So it allows us to categorify the stable envelopes on B side. At least that was one of my motivations why I tried to match this object on A side with something on B side. Okay. Thank you for all for your attention, and thank you for inviting me to speak on this seminar.
Thank you very much. So questions?
I have a lot of questions. It's very nice talk.
Try to ask them before the midnight. Yes.
I won't take. I want to just ask two. One is these pictures at the end that you're drawing of these excuse me, of these Lagrangians. So you're going to infinity like positively and negatively, but there's these points that they're coming from are, I'm to understand them as being sort of holes or punctures, yes, in the space.
So the crosses are punctures,
yes,
but my points run over this cycle. So in this picture, for example, if I look at this picture, I'm working where I have pairs of points, and one points run all the values along one line, and the other runs along the other one. So it's a picture of two-dimensional Lagrangian in real 4 dimensions.
Yeah, but my question is sort of there, but there is some, do you have some kind of compactification here? I mean, you have a non-compact Lagrangian, and you're talking about
Yes.
a wrapped category. And I'm just wondering, near this kind of punctures, what is there some wrapping there, or is there some?
There is wrapping.
I
But
see.
surprisingly, you can express what happens to Holmes under this wrapping if you localize.
Yeah, that makes actually.
I can show how to do it, but yeah, just it's a couple of pictures.
Yeah, like some kind of spiral kind of things or something.
Yeah, but you basically like let me try to write. So if you want a cycle like this, you can, so it's relative to infinity, it's relative to this thing. So I can say that it's no different, let me use a different color. It's no different than saying that I will take this guy and then push it here. And this guy should come with a factor of like 1 minus chi, where chi is the monodromy. So basically that's the same thing as infinite wrapping you have in the wrapped Fukaya category, where each thing is like, if here it's 1, it's chi squared, and so on.
And is there an action of the sort of the cohomology of a pointer? What is this coming from these?
It comes from monodromies of local system. So monodromies of local system have 2 parameters, and once I wind around this thing, it comes to the next branch, which differ by a chi. And if I think that chi is sufficiently generic, I can make sense what this is, just purely algebraically. Or if I think that analysis works and it converges, I have this interpretation, which is exactly the wrapped Fukaya thing. But if I just want to keep the story algebraic and don't care which characters are big, which characters are small, I can write this always. And you see like the Holmes computed by between 2 things that escape to infinity. If I want to make a consistent definition, I will be forced to always allow wrapping, or else I'm trying to intersect 2 Borel-Moore classes, and that's an ill-defined thing. I should intersect Borel-Moore with a compact version. So making a compact version is exactly making wrapping in categorical language. So yeah, surprisingly, like after I drop away all category stuff, it still works on the level of algebraic topology.
Nice.
That's a well-defined model.
Okay, well, so I as I said, I have a lot of questions, but maybe I'll hold them for
you can email, I think. Yeah.
Okay, thanks for the talk.
Yeah, all right. More questions? So do I understand correctly that when you your B side is holomorphic symplectic, and you have this stable envelope which is kind of Lagrangian, and when you categorify, you get some sheaf with supported on this whatever. I'm not sure, sheaf or maybe complex of sheaf. Well, let's speak about sheaves.
Object of derived category, let's say.
Yeah, technical object. Yeah, now my question is that since it's symplectic, I can quantize it. And so these Lagrangians, it quantizes to probably an object in the derived category of holonomic modules of the quantized algebra or sheaf of algebras on the symplectic manifold. So on the B side, what do you do with Fukaya-Seidel?
On A side with Fukaya-Seidel,
on the A side, So without potential, I would say that you just deform the symplectic form. But with potential, probably something should happen, and I'm not sure what.
I'm also not sure what it could be, sorry. I didn't think about that direction.
Okay. More questions? Well, if there are no more questions, well, thanks Yixuan for very interesting talk. Yeah, thank you very much. And
Thank you.
this is it for today.